Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process from Mahatma Gandhi, who is the father of nation. He says that you must not lose faith in humanity. Humanity is an ocean. If a few drops of ocean are dirty, the ocean doesn't become dirty. It's a very important and profound statement when humanity is at stake at this moment. We need to repose the faith in humanity and work for the humanity in ourselves and also among other fellow beings. And we can now recall what we learned in the last lecture. If you look at, we started the discussion on looking at various structures in both overexpanded nozzle and underexpanded nozzle, and then we also derived an expression for the thrust coefficient. And if you remember well, the thrust coefficient is a very important performance parameter, particularly for judging how good the nozzle is, and it is a function of pressure ratio, that is PE by PT2, and it is also function of PA by PT2, and area ratio and gamma. And by knowing all these parameters, one can evaluate theoretically, but however one can also evaluate experimentally by measuring the thrust and the cross section of the throat and chamber pressure, that is PT2. Suppose you know the thrust coefficient, or you assume certain thrust coefficient for designing a rocket nozzle, then you can very easily find out the thrust by knowing the thrust coefficient CF, and the AT is your throat area and PT2 is your chamber pressure. If I know all these parameters, I can very easily evaluate the thrust. And let us discuss little bit about the thrust coefficient. You can recognize there are two distinct terms over here on the right hand side of this equation, and this portion is basically momentum thrust, and this portion is your pressure thrust. And keep in mind that this PE by PT2 is a parameter which will be dictating what is AE by A star, or AE by A star will be dependent on the expansion what you want to have. Of course, one can notice here when PE is becoming small for a particular chamber pressure, this pressure thrust term, or the pressure thrust coefficient due to the pressure thrust, will be decreasing, and the thrust coefficient due to the momentum change will be increasing, because these terms will become a smaller values P by PT2, and then this thrust coefficient due to the momentum change will be increasing. And of course, there is a situation where you will get maximum thrust coefficient. That is possible only when the nozzle is expanded fully. That means the exit pressure must be same as that of the ambient pressure or the back pressure. So, that means we can achieve the maximum thrust when nozzle is fully expanded. Then as a result, these terms will be 0, and then the optimum thrust coefficient becomes Cf naught, we are saying this is the optimum values, is equal to root over 2 by gamma plus 1 power to the gamma plus 1 divided by gamma minus 1, 2 gamma square divided by gamma minus 1 in the bracket 1 minus P e by P t 2 power to the gamma minus 1 divided by gamma. Keep in mind that this optimum thrust coefficient, this is your basically this optimum thrust coefficient is a function of gamma, and it is also a function of P e by P t 2. Let us consider 3 gammas and plot that Cf naught versus the P e by P t 2. You can see that for a particular gamma, let us say 1.4, you can see Cf value attains a very higher value when it is maybe around something 0.001, that is P e by P t 2, means the exit pressure is very low as compared to the chamber pressure, and this situation can occur at higher altitude, and of course it decreases at a very faster rate, very high slope over here, and then after that slope decreases and it decreases slowly. And the similar trend you can see for the gamma is equal to 1.2 and gamma for gamma is equal to 1.1. However, the increase in Cf value or the optimum thrust coefficient can be seen here. Interestingly, you can see that higher P e by P t 2, this value let us say at 0.1, there is not perceptible changes in the value of Cf naught. That means it is not really changing much. The effect of the gamma at higher pressure on the optimum thrust coefficient is negligibly small. However, when the pressure ratio decreases, then this effect goes on increasing and it becomes quite substantial at a very low pressure. Let us say P e by P t 2 is equal to 0.001 at the axis origin, that because this is increase is exponential. Of course, this is not very much easily observed in this figure because it is all merging to the axis. However, if you plot this figure with respect to log of Cf naught versus the log of P by P t 2, you will find there is a substantial changes in Cf value with the change in gamma. And another things you can see from this expression, that when P e is decreasing, then this value will be basically having very less and this very small values, and this 1 minus of that is becoming increasing. This term is tending towards 1, that is the maximum value one can think of when the P e divided by P t 2 is equal to 0 or tending towards 0. That means, if P decreases, maximum thrust increases. When P is equal to 0, then Cf attains a maximum value for a fixed specific heat ratio. So, if you look at this term, is goes towards 0. So, you will get Cf naught is equal to root over 2 by gamma plus 1 power to the gamma plus 1 gamma minus 1 and 2 gamma square gamma minus 1. This is the expression one can get is the maximum Cf naught. So, you can see that basically it is a function of gamma only, and another interesting feature one can see from this, that for maximum thrust coefficient we should have very higher chamber pressure and lower values of the gamma. Of course, the higher chamber pressure means you should have a very thick wall kind of things, and because the temperature in the thrust chamber will be very high, and you should use very good materials that can withstand not only the stress due to the pressure but also due to the temperature. So, therefore, one has to choose the chamber pressure properly, although it is always desirable to have higher thrust coefficient. As I told earlier that thrust coefficient plays a very important role in so far the performance of the nozzle is concerned, because there is no term temperature over here, and temperature generally will be generated in the thrust chamber, and of course with the due to the combustion of the propellants, and it also increases the pressure in the thrust chamber. And of course, let me repeat little bit that you can estimate very easily by measuring the thrust F and also the chamber pressure PT2 and the throat area of the nozzle of the rocket engines. So, therefore, you can evaluate experimentally CF values, and using the right hand side expression you can very easily also find out theoretically, that we will be using, and the experimental values need not to be same as that of the theoretical value for the same pressure ratio across the nozzle, or in other words for a particular area ratio. Let us look at this expression little further and see what is happening. If you look at this expression, that Cf is basically function of Pe by Pt2 and Pa by Pt2 and Ae by A star and gamma specific heat ratio, and Ae by A star we know this expansion ratio. And if you look at this, Ae by A star is dependent on Pe by Pt2. So, therefore, we will be now looking at how does this Cf, that is thrust coefficient, is varying with the area ratio and with also with Pa by Pt2 for a particular gamma, that we will see how does these plots will be looking like that. And this is your plot which I have shown here, that is your thrust coefficient Cf is plotted on the vertical axis. On the horizontal axis, the area ratio epsilon, which is equal to A divided by AT. AT is basically choked throat area. Sometimes we call that AT is basically A star, because the choked conditions we are looking at. And this, if you can see that it is being plotted for Pt by Pa, and starting from the 2, that is the pressure ratio across the nozzle 2 to the something around 1000, and keep in mind that as I told earlier that AT is a function of P by Pt2. So, therefore, there is no need to really look at the P by Pt2, already we have considered that in terms of this area ratio. So, you can see that there are a lot of lines, and this is being plotted in the semi log plot. You can say this is the log scale on the horizontal axis. Let us consider one of the pressure cases. For example, Pt2 divided by Pa is 5. You can see that this thrust coefficient goes on increasing with the area ratio 1, and it, as the area ratio increases, it can go like that, which I have not shown here. And keep in mind that at the area ratio of 1, this attains maximum value, that is the thrust coefficient around something 1.09 something here, and this is area ratio is equal to 1.5. And when the area ratio decreases less than 1, you can see that the thrust coefficient decreases, and because of fact that this is area is being lower than the for which it is particularly designed, so that the pressure will be expanded less. That means PE at the exit will be higher than the back pressure or the ambient pressure at which it is for which it is designed. As a result, there will be expansion of gas downstream of the nozzle exit, and this we call it as a under expansion, as further expansion needs to be undergone as the pressure PE is greater than the back pressure PA. And we have already learned how the structures of the flow structure at the downstream of the nozzle exit will be for under expansion, and there will be expansion fan emanated from the lips of the nozzle exit, and then it will be interacting with the boundary layer and then reflected back as a series of compression wave which coalesces into shock. And again this shock will be impinging into the jet boundary, and then it will be again reflected back as a expansion wave. Of course, before that there will be a MAC disc at the center line of the nozzle, and this shock cell will be goes on formed. The shock cells will be formed as long as the strength of the shock cells will be decreasing, and this pattern is quite complex in nature. As a result, there will be decreasing the thrust coefficient, and if you go just opposite direction, that means when the area is increases, that become let us say 2, then there will be also decrease in the thrust coefficient, because of fact that this pressure PE will be less than the ambient pressure, and it is basically over expanded. As a result, that it has to undergo the oblique shock and sometimes the normal shock, depending on the pressure ratio what it will be there. And as a result, there will be, of course, the shock will be emanated from the lip of the nozzle exit, and then it will be reflected back as expansion wave. Then the MAC disc will be formed, and then there will be again coalesces into the shock wave, and further downstream this shock cell will be continuing to be formed till its strength is decreased or diminishes. But however, if you go a little beyond certain limit, like here that point, then there will be flow will be separated in the conical nozzle, even in the bell shaped nozzle, and as a result you cannot operate beyond that, because the losses will be very high and the thrust coefficient may decrease drastically. And this is the point where the maximum thrust coefficient you can obtain for a particular PT2 by PA of 5, and of course, if you decrease the pressure to 3.3, there will be decrease in the thrust coefficient. If you look at this is the maximum values, and if you go to 2.5, there will be decrease in the peak thrust coefficient value as the maximum thrust comes in lower values, and it goes on. But if you goes on increasing to the pressure PT2 by PA, then you can see that there is a substantial increase in these CF values, and if you go to the 20, again there will be substantial values of the peak CF coefficients, and it goes to the, if you go to 33 point, there is also increase, but if you go beyond 33 point pressure ratio, that is PT2 by PA, then the increase in the peak thrust coefficient decreases or diminishes out as you go on this increasing the PT2 by PA. Therefore, practically the people always try to restrict this pressure ratio, the PT2 by PA of 33.3, because you won't gain much from the increasing the pressure ratio across the nozzle, because if you increase this pressure, then naturally the thrust, the area ratio will have to increase to get a peak values of the thrust coefficient, and then with increase in area ratio, the length of the nozzle for a particular angle, it will be increasing. So also the thrust, so the weight of the engines will be also increasing. And if the chamber pressure increases, then you will have to pay the penalty for using very good quality material, and beyond certain limit it may not be possible to have within the constraint of material what we are having at this moment. So, however, theoretical, when you look at this, pressure can go up to very higher level. You can look at the 2 here, this CF, that is thrust coefficient value of 2 you can get, which is not shown in this figure, around area ratio of 200 and this pressure ratio of 10,000. And when this PT2 by PA goes to infinity, that means chamber pressure is very high and PA is tending towards 0, right, then it become infinity values, and at this condition the CF value happens to be 2.246 for gamma is equal to 1.2, and of course, which is not shown in this figure. And keep in mind that when you join these peak values of each pressure, you will get the line of the optimum thrust coefficient, that this is the line, and of course, for each pressure ratio, the point beyond which the flow separation will be occurring, and this is known as the region of flow separation of the conical nozzle. So, as I have already discussed that this is a very important one should understand. Let me repeat little bit about the under expansion when it is occurring. That is, if you look at a conversion diversion nozzle, let us say with the area ratio of AE, and this is your A star, and for that it is being plotted the pressure, and P is decreasing, as you can see, along with the x direction, and this is your x direction, right, and you can see that this is the pressure at the throat region when it is choked conditions. Keep in mind that this is very smooth or it is decreasing monotonically, but however, in practical situation there might be little bit kink over here, because of fact that the sonic wave will be on the occurring at the throat. So, therefore, there will be, but in we are considering the theoretical one, therefore, there is no need to have this form. And keep in mind that if it is expanded fully, that is P is equal to P A, you will get, but if you are using a shortened nozzle, then you will get that P E, and this P E is basically greater than the P A. Therefore, there is a need for expansion to be taking place beyond the nozzle exit. So, we call it basically under expanded. And if let us say there is a you are now operating in such a way that the pressure ratio for which you are basically having a increase in area, so that you will say that this will be the expansion will be taking place beyond that. That means, this P E is less than the P A for which it is designed. So, therefore, this portion is basically is the over expanded portions, and one has to avoid that one. As I told earlier, when P E is greater than P A, it is under expansion, and when P is less than Pa is the over expansion. This is basically over expansion. And keep in mind that this pressure ratio has to be proper, so that the oblique shock formation leading to the flow separation can occur at a P by Pa less than 0.4, and this is, we have already discussed, this is basically the Summerfield criteria. It must be used for designing a rocket engine such that the flow won't be separated out. As the shock is being formed, oblique shock, then the pressure will be very high over here at the downstream of the shock, and then the flow is likely to be separated from the wall surface. Of course, there are various reasons why separation will occur, but this is the important point that must be kept in mind, and otherwise the due to the flow separation, the thrust level will be reduced drastically, and then of course we can reduce the thrust coefficient. And with this we will stop over here, and we will be discussing further about various aspects of the nozzle in the next lecture. Thank you very much.